So I'll say claim now is that S does not contain T. And so let's really think of what this equals. This is saying that, or this is equivalent to, that S, it does not contain T, right? Not S contains T. And S contains T, remember what that's saying, is that for all X in T, X is an S. But we're saying this doesn't happen. We're saying the opposite of for all X in T, X is an S, which must mean that there exists an X in T, not an S. Otherwise, every X in T would be an S. So this must mean that there exists an X in T such that X is not an S. And by the way, you can think of it the way I just thought of it, or you could just like mechanically go through and negate this, right? Because you negate this quantified statement, you flip the quantifier, negate the predicate. Remember that whole thing? Yeah. So the opposite of S being disproving. So saying that S is not saying that T is not a subset of S. S does not contain T. Those two things are the same. Saying this is the same thing as saying there must exist something in T, not in S. Otherwise, S would contain it. Here's the proof. How do you prove an existential statement?
You just find a counterexample?
You just find an example. Yeah. Counterexample is like if you're trying to prove something. So if I said S, it contains T, then to disprove that, we'd find a counterexample. But in a weird sense, my claim is S does not contain T. So that's just an example. We're splitting hairs. Yes, you're exactly right. We're finding an example. So let's go ahead and let X equal, you could pick any number, any odd number that's not a prime, right? Because T is a set of primes, S is the odd prime numbers that are greater than or equal to 3. So if we just find one odd number that's not a prime, we'll show that this is not contained in this. Not everything here is a prime. So why not let X equal 9? So remember the existential proofs. The first thing we do is verify that the X we pick is in fact in the domain we want it to be. And the domain here is T. So note 9 is, so note 9's an end. And 9 equals 2 times 4 plus 1. So 9 is odd. Thus, 9 is in T as required. However, 9 also equals 3 times 3. I'll say, however, by observation, nine equals 3 times 3, and 1 is less than 3, less than 9. Thus, 3 is a non-trivial divisor of 9. Hence, 9 is not prime. So this is the problem going the other way, Herman. It just doesn't work because you can find odds that aren't prime. And I see what you're saying though, because odds, it feels like a bigger set than the primes. The primes feel more sparse. We shouldn't necessarily be thinking about bigger and smaller. We should be thinking about inside and outside. And so we can do some more examples later where there's some sets that it's not really clear. It doesn't really make sense that one would be bigger than another, but it does make sense that one contains another. But anyway, so 9 is not prime. Why do we care about that? Therefore, there is an element of T, mainly X equals 9, such that X is not in S. So T is not a subset of S. It's not blocks. I went too quickly. There we go. Make sense?
Yes.
Perfect. Yeah. So here's how you prove that something's not a subset of something else. You just show that there's one element that's in this, that doesn't, to show A is not a subset of B, so there's one element of A that's not in B. Therefore, B does not contain A, because at least that one little element pokes out. And this will be an interesting time to talk about Venn diagrams.